Okay, I want to introduce the idea of reaction forces now. This is pretty natural, actually, but statics problems often include some kind of member that's hinged or pivoted or in contact with some surfaces. And when this happens, you need to include the reaction force to the member. So what force is being exerted by that hinge or that surface or that pivot because of the presence of the member? So often people will just draw in an Rx and an Ry to represent the Y component and the X component of the reaction force, solve for those, and then possibly figure out the magnitude and direction of the reaction force at the end. So I have a simple example to introduce the idea of reaction forces. Okay, so up in the corner here, we have this picture where we've got a pin-connected truss. You can see the pivot point there, and you can see the values of some of the forces. So it says if F1 is 35 newtons and F2 is 68 newtons, find the force F3 required to create equilibrium. Also find the vertical and horizontal reaction forces exerted at the pivot point. Okay, so our structure this time is a little more complicated. It looks like this. And the forces that are acting, I'll put them in a different color. We've got F3 here. We've got F1 here. We've got F2 here. And then there are going to be some reaction forces potentially at the pivot. So we could draw Rx going this way, Ry going this way. Again, if you get the directions wrong, you'll just get a minus sign. You'll be able to correct it in the end. Okay, there's also, and this is going to be our axis of rotation. It is the pivot point. It's actually marked. It would be quite unnatural to choose somewhere else as your axis of rotation. So we'll imagine rotation about there. No, there are lots of distances that we often want to include on our diagram. So let me do that this time. So this distance here is 3. This distance is 4. And this distance is also 4. And we'll assume that those are in meters. Okay, so here we want to say that the net force is equal to 0, and that means that we have to set it to 0 in the x direction and the y direction separately. So in the x direction, let's see, we only have 2 forces in the x direction, Rx and F3. So that tells us that Rx, and I'll make it negative Rx plus F3 equals 0. So it follows then that Rx is equal to F3, but we don't know what either one is equal to. Once we figure that out, we'll be able to answer 2 parts of the problem. Okay, so that's equation 1. Now we also need to set the sum of the forces in the y direction equal to 0. So we've got F1, F2, and Ry there. So that's going to be Ry minus F1 minus F2 equals 0. So that tells us that Ry is equal to F1 plus F2, and we know those values. That's 35 and 68. So Ry then is 103 newtons. That was one of the things we were supposed to find. Okay, so we've got that. Now we need to do some of the torques equal to 0. Okay, we'll do them about this point here, which I should have labeled O. All right, so the reaction forces Rx and Ry can't exert torques about that axis because they're acting at that axis. So we're just going to have 3 torques to consider, the one from F1, the one from F2, and the one from F3. So let's start with the one from F1. It would cause a clockwise torque, so I'm going to put a negative sign on it, and it's going to be 4 times F1. Actually, I know the number for that too, but I'll put it in later. Now the torque from F2, well, it's located 8 meters away from the axis of rotation. So that's going to be 8 times F2. And then F3, let's see, it would contribute a positive torque. It would make it go counterclockwise. So it gets a plus sign. And I'm going to do 3 times F3. and all that is equal to 0. Now, since I have values for F1 and F2, I can easily figure out what F3 is. So I'm going to get 4 times 35 plus 8 times 68 divided by 3. And that gives me 228 newtons. Okay, so we figured out that F3 is 228 newtons. So that was one of the things we were supposed to find the force F3. We were also supposed to find the vertical and horizontal reaction forces, sorry. So we found our Y, and then using equation 1, we can see that Rx is equal to F3 is equal to 228 newtons. So we found that as well. Okay. So far in this section, we've had all forces that were at 90 degrees to the line between where the force acted and the axis of rotation. But sometimes forces act on funny angles, so you need to remember how to apply these different ways of thinking about torque. So you can think of torque, if you remember, as the moment arm times the force, or as R times the perpendicular component of the force. They're both going to boil down to this, R times F times sine theta, where theta is the angle between R and F. You can also use the cross product version. But for most problems, I think you'll find very often this one is the easiest, sometimes the one underneath. Okay, but they all boil down to the same thing. So you can do kind of what you prefer. Okay, so this one we've got a bear going for goodies, and he's walking out on a beam, and he weighs 700 newtons. The beam is uniform, weighs 200 newtons, and has a length of 6 meters, and the goodies basket weighs 80 newtons. Okay, so when X is 1 meter, so that is when the bear's center of mass is 1 meter from the wall there, find the tension in the cable and the components of the force exerted by the wall on the left end of the beam. So that last bit, they're asking us to find the reaction forces in this area. Okay, so we start by drawing a free body diagram of the beam. So here it is. Now we're going to have reaction forces at the left end. Maybe I'll put this in another color. So we could have Rx and Ry. We're going to have the weight of the bear on the beam. So I'm going to call that F1, and that's 700 newtons. We're going to have the weight of the beam itself, just be located in the middle since it's a uniform beam. So that's F2, that's 200 newtons. And then we've got the goodies basket, which is right at the end. I'm going to call that F3. It's 80 newtons. And then we've got this tension force. I'm just going to keep with the numbering. I'm going to call it F4. We could call it T if you want. And this angle here is 60 degrees. Okay, let's put some distances on here as well. So the whole thing is 6 meters long. And that means that this distance here is 3 meters. And this distance was 1 meter. And I think that's all we need to know. Okay, so there's the free body diagram. And then we can start using our equilibrium equations. So our first equation of equilibrium, sum of the forces in the x direction equals 0. We're only going to have 2 forces for that. We're going to have Rx, and we're going to have a component of F4. So F4 cos 60 equals 0. So that gives us Rx equals F4 cos 60. We don't know what either one of those forces are still, but we have a relationship between them. So if we get one, we can easily find the other. Okay, the forces in the y direction also sum to 0. So this is going to be a bit more, it'll have more steps in it. Ry minus F1 minus F2 minus F3. And then there'll also be a component of F4 that will go upwards. So F4 sine 60, and all that's equal to 0. So from that, you can get a few things. You can get that Ry plus F4 sine 60 equals the sum of F1 plus F2 plus F3. And that means that Ry plus F4 sine 60 equals 980 newtons is what that works out to. 700 plus 200 plus 80. So that gives us another equation. Again, we didn't get any answers from this. We're just getting relationships. So it's important not to get frustrated, to realize that's the way these problems go. Okay, before we go on to doing the torque equation, well, we're going to need this image for the torque equation, right? So let's pick an axis of rotation, and I want to do that in red. And I'm going to pick the left end, which is my favorite place to choose my axis of rotation. You can do it anywhere, but I find the left end just makes it really easy for me to read off the distances and remember what place I've chosen. And it's a good place to choose because there are two forces acting there, and I'm not going to have to include either one of them in my torque equations. So it's going to make the math a little bit easier too. Okay, the next step is to let the sum of the torques equal 0. So we're going to have 1, 2, 3, 4 torques from forces 1, 2, 3, and 4. As I mentioned before, no torques from Rx and Ry because of how we chose the axis of rotation. Okay, let's start with the torque from force 1. It's going to contribute a negative torque because it will cause a clockwise rotation if just that force alone were acting. And it's at a distance of 1 from the axis of rotation. So that'll be -1 times force F1, which is 700 newtons. And now let's take into account F2. It will also contribute a negative torque. It is acting 3 meters away from the axis of rotation. It's going to be 3 times 200. And then the basket, we can do that. It's 6 meters away from the axis of rotation, also contributing a negative torque. And then F4, it's going to be all different. It's going to cause a positive torque. We don't know what the value is. And there's also this angle to worry about. So a couple ways to tackle this. Well, first let's put in the I'm gonna use for torque 4. I'm gonna use R times F4 perpendicular. Okay, you can do it lots of different ways, but that's what I'm going to choose this time. So I'm going to draw in a dotted line here, and this is going to represent my F4 perpendicular. And that's going to be equal to F4 sine 60. Okay, so let's put that into our equation. So I'm going to do R, which is 6, times F4 perpendicular, which is F4 times sine 60. And all of that is equal to 0. Okay, so I can solve now for F4. So let's see, we'll have 700 and 600. Oops. And this works out to 343 newtons. And now that we have it, we can sub back into our other equations and get the rest of the answers. So let me do that. So from the first equation that we had Rx equals F4 cos 60. So we can put in our 343 times the cos of 60 and get 171 newtons. And then from the second equation that we used, from the second equation that we came up with, we had that Ry plus F4 sine 60 equals 980 newtons. So we can find our y now. It'll be 980 minus F4 sine 60. So that's 980 minus 343 sine 60. And that works out to 683 newtons. There's a part B to the bear problem. It says if the cable can withstand a maximum tension of 900 newtons, and we found that the cable last time only had 343 newtons, what is the maximum distance that the bear can go before the cable snaps? In other words, this will let us find out if the bear gets to the goodies or not. Because if that distance is less than 6 meters, then he didn't get there. Okay, and we don't really have to redo the whole problem to do this. We had a formula for the net torque, right? We'd worked out what the net torque was in terms of all the different forces and distances. And all we really have to do now is rethink that equation with F4, the tension, being a fixed number, and the position of the bear being a variable. So all that's going to happen now, I'm still going to think of my axis of rotation as being here. And well, I'll have minus x times the force of the bear. That was F1. It's my first torque. And then I'm going to have minus 3 times the weight of the beam itself. That was 200. And then minus 6 times the weight of the goodies basket, which was 80. And then plus 6 times F4, which is 900, times sine 60. And this is going to be equal to 0. Okay, so this is just the equation that we had before, really, except for before this was a variable and this was known, and now they've switched. Okay, so you can solve this for x. Rearranging for x here, let's see, we get 6 times 900 times sine 60 minus 3 times 200 minus 6 times 80, and then we have to divide by F1, which was 700 newtons. And then we can throw this into a calculator, see what we get. And you should get 5.1 meters here. The bear does not get the goodies.